Alrighty, can everybody hear me? All right, so good morning and welcome to week 2 of 6.S184/6.S975. This is our last formal lecture. Next week will be 2 guest lectures, which we want everybody here for as well. But yeah, so today we're essentially going to be wrapping up sort of the framework that we've been building throughout the past several lectures, and turning our attention from unconditional generation, which is generate something, to the task of conditional generation, which is generate something given some preference or auxiliary information about what we want to generate. And specifically, we're going to be focusing on this sort of prototypical running example that we've been using of image generation. So without further ado, let's get into it. Again, feel free to stop me if you have questions at any time. Yeah, just raise your hand. So, OK, recall. What have we been thinking about so far? We've been thinking about what I'm going to call conditional generation for the next few slides. And what does conditional generation entail? Well, the problem is essentially I want to sample from p-data. So p-data is the distribution of images, or the distribution of 3D meshes of video game characters, or 2D samples from a checkerboard pattern, like in the lab. And we've developed these training objectives, such as this conditional flow matching objective, that allow us to train a model for this marginal vector field, ut theta of x, by regressing it against this conditional vector field, ut target. And notice I've put this conditional flow matching objective here. We've also developed these denoising score matching objectives that are kind of analogous and allow us to extend results for flow models to diffusion models. In this lecture, we're really going to be thinking about flow models. All of these results can be extended to diffusion models, but just to kind of contain the narrative of the lecture today and just sort of prevent clutter, we're just going to stick with flow models, and then you can take a look at the notes to see how they might be extended to diffusion models. Right, OK, so we can train a model ut theta using this conditional flow matching objective, and then we can sample. And again, this is kind of what we've been talking about for the past week. We can sample by simulating the corresponding ODE. And again, if you were to train the score with denoising score matching, you would obtain an SD as well. We simulate this thing from 0 to 1. And we, in theory, would obtain samples from our data distribution if our model was learned perfectly. Right, OK. But like I said, this is unconditional. And the problem that we care about is conditional generation. So what does this mean? Before we get into that, I think this is a good segue into our agenda for today. So broadly, we're going to be extending our work on unconditional generation to this conditional setting, going from generate an image to generate an image of a dog baking a cake, or something like that. We're going to develop a particular technique for sampling in this conditional setting, known as classifier-free guidance, which is widely used in practice. And then we are going to discuss architectural choices for this running example we have of image generation. And we're going to survey some current models, namely Stable Diffusion 3, which is a flow matching model. And then at the end, we are lucky enough to have a guest talk by Carls, who will talk about alignment in diffusion models. So without further ado, let's get into conditional generation and guidance as well. And again, if you have a question, raise your hand, and we'll discuss. OK, right. So what have we been talking about so far? We've been talking about, we've been asking questions of the form generate an image. We've been asking our generative model nicely to generate an image. In practice, often what we want to do instead is ask our model to generate an image based on some textual prompt or based on some additional information, like a label, for example. And up here, we have images sampled from Stable Diffusion 3. It's this scaling rectified flow transformers for high-resolution image synthesis. This is the Stable Diffusion 3 technical report. And we have these 3 prompts paired with these wonderful captions. The first is a swamp ogre, these pearl earrings. We have a car made out of vegetables. And then we have this line drawing of the heat death of the universe. And really what we're going to be asking ourselves is, we've been generating samples from 2-dimensional distributions, little checkerboards in 2 dimensions. And some of you have been coming up to us in office hours and asking, well, this is great, but how do I actually generate things like this? And today we're going to be bridging that gap. And as we'll see, we're actually not very far from this. And the difference between where we are right now with our conditional flow matching and score matching objectives and being able to generate images like this based on prompts or based on other labels like this is essentially just we need to sort of characterize some mechanism by which we might sort of condition or guide our model based on these prompts. And then we need to develop, we essentially just need to scale up our UT of theta to something that you would encounter in practice. And as a preview, an MLP will no longer be sufficient. But beyond that, we're nearly all the way there already. OK, so before we go any further, you've noticed that I've used the words unconditional and conditional, which sort of in an effort not to overload these terms, we're going to instead refer to them as unguided and guided generation, right? Because we've been talking about conditioning on Z, for example, and now we're going to be talking about guiding on Y, guiding based on Y. OK. Right, so we're in this guided generation setting. We're conditioning on Y. So Y here might be a text prompt, an ogre with a swamp ogre with pearl earrings. Y might be a class label like apple or banana. In lab 3, Y will be a digit. We'll be working with the MNIST data set of handwritten digits. And right, so Y can take all different forms, but in general, we're going to be sort of guiding based on Y. So how does our notation change? On the left side here, we have the sort of unguided terminology that we have been working with so far. And on the right, we have the guided notation here. So essentially, you can obtain the right side by prepending the left side with the word guided. And this takes the form notationally of using this conditioned on Y terminology. And again, I just want to stress that formally, guiding is just conditioning on Y. Right, so our marginal probability path becomes a guided marginal probability path. And similarly, our vector field becomes this guided marginal vector field. And we can define the marginal score, and the guided marginal score. Sorry, we can define the guided marginal score, the guided model in the same way. And then just as we had this conditional flow matching objective to train our unguided model, we are curious as to what the guided analog of this would be. If I'm trying to train a guided model, how might I adapt this conditional flow matching objective for this guided setting? So this is a question we're going to sort of be starting with first, and for which I'm, what happened to my animations there? All right, let's go to the board. Right, so what are we thinking about right now? We are thinking about a guided flow matching objective. This is where we'll start. So a guided conditional, I'll say, flow matching objective. Okay. So we're essentially going to be making an observation. And what is that observation? It's that if I fix Y, then I'm only really caring about one target, which is p data of x given this fixed Y. Then I essentially recover the unguided problem that we've been thinking about so far. Does this make sense? See some head nods? Let me keep writing. And observation. OK. So if I fix Y, we recover the unguided problem. All right, so we might think then that we can construct a sort of CFM-esque objective with this fixed Y. So let's define, let's just start writing and we'll see what makes sense. So OK, let's call it LCFM. And then maybe I want to stick, let's call it guided, because again, there's a Y kicking around in here. And this is a function of sort of this parameter theta as well as this hyperparameter Y, which is the fixed Y. OK, and what is this? Well, this is an expectation. It's an expectation over something. OK, we'll look at what the something is in a sec. And well, what are we regressing? We're regressing our guided model. So this is ut theta of x guided by Y. We're regressing it against, this is a conditional flow matching objective, against this conditional vector field, ut target, x z. And I'm taking the squared magnitude of this guy. Right, okay, so this is an objective. This kind of makes sense. Instead of regressing just ut of x, I'm regressing ut of x given y. And what am I taking the expectation over? Well, I'm taking it over. I want to sample z from p data. But is it just p data of z? No, now it's p data of z conditioned or guided by y. I'm sampling t again from this uniform distribution on 0, 1. And then I'm going to sample x from this conditional probability path of x given my choice of z. And again, this is the same. Is everybody happy here? OK, but y is fixed, right? That's no good. We want to be able to vary y. And so what we're going to do is we're going to say, let's make another observation. Observation 2. OK, now let y vary. And again, I'm going to have a slide in a sec. You can take a picture of the slide. The slide will have this in LaTeX. OK, so now if we let y vary, then OK, this is going to be, let's call this LCFM guided of, now it's just theta, right? We're no longer fixing y. This is going to be an expectation over some square, of sort of this difference, this term here, which is just the same. OK, but the change happens. What is square? So what do I have to change with square? Sample y. Right, so now we have to let y vary. OK, so really it's this guy that needs to change, z from p data given y. So instead, we're going to be thinking, we're going to sample z and y from this joint distribution over p data of z and y. OK, so this is sort of a conceptual leap, right? Now our target distribution is actually a distribution over both z and y, right? So if you're thinking about implementation, this would be a data loader that returns you image and label, or image and text prompt that corresponds to it, right? So our notion of what the target distribution is now sort of encompasses what the label is as well. And then the remainder of these guys, 0, 1, and I'll move in a sec, so I'm not blocking the board here. These guys are all the same. This is sampled from this conditional probability path, like that. OK, we have our guided objective here, where this is the same as here. Let's go to the next slide, which just formalizes this. Oh, OK, there's my animation. I don't know what happened to the other one. Right, so just to summarize, for fixed y, we can obtain this objective, which is basically just conditional flow matching. And then by varying y, we can actually obtain the desired effect of regressing against all such y, or sort of amortizing over all possible choices of y. And really, kind of, we've already done all the hard work in developing our conditional flow matching objective. It is now simply a matter of just extending it over y, which is, as it turns out, sort of the easy part. OK, great. So what can we do with this? We can use this to train our guided vector field, ut theta x, y. And then we can sample. And the sampling is, again, not very different than how we did it when it wasn't guided, or i.e. in the unguided setting. So what are we doing? What do we need? We need a trained guided vector field. This guy, ut theta of x, guided by y, or conditioned on y. And then when we sample, we select a prompt y. Again, y lives in this /mathcal_y world of y's. And this could be something like a cat baking a cake. It could be the digit 1, as we'll see in the lab. It could be anything that makes sense. Depends on the context. We're going to initialize a starting distribution from this initial distribution, p init. And then we're going to simulate the corresponding ODE. If we were working with SDEs, check the notes for the generalization to SDEs. We would analogously, we would sort of consider a stochastic differential equation. Here we're considering this ODE. So we simulate it from 0 to 1. This is kind of the same thing that we've been dealing with in the unguided case. And then at x1, we obtain our samples. OK, so this is sort of the critical transition point between guided sampling and what I will discuss next, which is classifier-free guidance. But I really want to stress that this is sort of, at least theoretically, kind of, we have already obtained sort of a faithful training and sampling procedure for this guided target. We are training this guided flow. This, if trained perfectly, this is the actual guided marginal vector field. If I sample and my model was learned perfectly, I would be sampling from the desired marginal target distribution, p data guided by y. But in practice, people don't actually sample like this. And the reason is that people noticed at some point that that you could achieve a certain trade-off in, I don't want to be too prescriptive here, but essentially you can sort of trade off diversity with perceptual quality with a technique called classifier-free guidance, which is what we're going to be discussing next. So classifier-free guidance is what you'll discover inside a lot of models, Stable Diffusion 3 included. And it is, we'll show you some pictures after we develop it of why this might be preferable. But let's dive into classifier-free guidance to start with. Let me start on the board. OK, so. All right, classifier-free guidance. So the following derivation we're going to be doing with Gaussian probability paths, which I'll write the definition on the board again. The result that we obtain is not specific to Gaussian paths, but the intuition that we will convey is specific to Gaussian paths. So what is a Gaussian path? So recall that a Gaussian what's a conditional conprob path is given by this conditional probability path. Pt of x given z is given by this normal distribution, and the mean of this normal distribution is alpha t times x, and the standard deviation, or sorry, the covariance of this distribution is given by beta t squared times the identity. And again, recall that where alpha t and beta t are these continuously differentiable cont diff monotonic functions satisfying. What do they have to satisfy? Well, they need to satisfy these endpoint constraints. So alpha 1 equals beta 0 is equal to 1, and alpha 0 equals beta 1 is equal to 0. Right, OK. So as it happens, we have the following, result for Gaussian paths. This is simply algebra. It's not very exciting to prove this, although you can. And in fact, a proof is in the notes if you're curious. But the fact is that we can relate the marginal vector field, the marginal guided vector field, and the marginal score, or the guided marginal score, in the following way. So we can say that the marginal guided vector field, UT target, of of x given y, well, it's going to be equal to AT, not alpha t, but ATX plus BT times what? Times the marginal score, or the guided marginal score. So log PT of x given y. OK, and what are AT and BT? AT and BT are sort of ugly. I'm going to write them on the right, where AT, BT are equal to, this is alpha t prime over alpha t, and this is, what is this guy? Let's see. I want to make sure I don't write this down wrong. is equal to alpha. And again, these actual values aren't super important for the derivation we're about to show you, but I just want to make sure I'm not writing these wrong. Minus beta t prime, beta t alpha t over alpha t. Right, OK. Great. OK, so cool. We have this relation that connects the guided target to the guided score. What we're going to do is we're going to recall Bayes' rule. So what does Bayes' rule say? Bayes' rule, well, it says that we're going to basically be expressing this guy. We're going to say, OK, well, this guided marginal score, pt of x given y, is equal to, we're going to rewrite pt of x given y via Bayes' rule. So this is pt of x times pt of y given x over pt of y. And I can sort of pull these out because this product and division becomes linear with the log. And notice that because this gradient is taken with respect to x, because this guy only because this only involves y, this guy's going to disappear. Or in other words, let me just actually write out that intermediate step. So this is log pt of x plus log pt of y given x minus log pt of y. And again, this guy disappears because there's no x, and we're taking a gradient with respect to x. Boop. Goodbye. OK, so I get that this marginal score actually decomposes into these two guys right here. So what does that give us? Well, slide the board up. I'm going to use that to rearrange our fact by plugging in Bayes' rule again. So I'm going to say fact becomes, or no, let's write plug in Bayes' rule. And we obtain what? We say, well, OK, ut target of x given y is equal to, what is it equal to? It's equal to a of t times x plus b of t times, well, we're going to plug in this expression right here. We're going to replace this guy with these two guys. That canceled. We get gradient, or we get this unguided score right here. Plus, we get this other term, which I'll come back to in a sec. It's pt of y condition on x, not x condition on y. All right? And what I'm going to do is I'm going to pair these guys up and then leave this guy off to the side, is equal to atx plus bt times the unguided score plus bt times this term right here. OK, and then, by our fact actually also applies when y is just nothing. This you may recognize as just ut target of x. So in fact, we have that this is equal to ut target of x plus this other term that we will soon turn to. OK, any questions there? Yes, no, maybe so. So all I've done is we've started with this fact right here. That's just a bunch of algebra. We have plugged in Bayes' rule, and we've obtained this equivalent form. OK, so I'm looking at this thing right now, and we're thinking, OK, so well, what can I do? I can say, OK, this is the term I care about. This is my guided marginal vector field. And it turns out this is obtained by taking my unguided vector field and then adding this term right here. And this term right here this is essentially providing all the signal of y, right? And furthermore, if we zoom in, we see that this is kind of this is sort of the likelihood of y given x, right? And because it's the likelihood of y given x, and because y might correspond to some sort of a class, y might be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 in the lab, we can think of this term as a sort of classifier. And again, this is purely intuitive. Okay, and the classifier is what is responsible for all of the signal for y. And so people had this idea that, well, let me sort of amplify the effect of my classifier. So let me deviate from the actual ground truth expression for uTarget. Let me deviate from the ground truth guided vector field. I think I can do a little bit better, in fact, by sort of overriding what the true theoretical guided vector field should be by cranking up the effect of my classifier. So what I'm going to do is I'm going to choose a guidance scale w more than 1. And what I'm going to do is I'm going to scale this term by w. Okay? And because I'm scaling this by w, it's no longer ut of target of x given y. It's no longer the actual guided vector field. It's going to be something else, which will denote ut of tilde x given y, which we are defining to be, well, it's ut of target as before, plus bt times our guidance scale times this classifier term. Right. OK, perfect. So this is an important conceptual leap. Tony. OK, right. So this is classifier is in quotes because it's intuitively a classifier-like thing. So what is it doing? It's telling us, so what is y? Y is like y is sort of a label or a text prompt. The term classifier might come from considering y to be a sort of class. You know what I'm saying? So maybe y is just some discrete object. Let's just think in terms of the lab. This could be 0 through 9, the digit identity in an MNIST data set. So this term is telling us, for a fixed x, what is the likelihood of y? So you can think of it's sort of telling us for each y what the likelihood is. And this is very similar to how you would implement sort of classifier as a distribution over the sort of possible bins that you could classify y into. Oh, that's a good point. Sorry, this should be like this. I mean, it could be like, we'll say it's like this. This is the classifier. We'll say. So, but we're paying attention, or maybe you could sneak the log term in there too, and the intuition would be the same. Does that answer your question? Okay, good clarifying question. Okay, perfect. But right, okay, so let's just make sure everybody's comfortable with this idea of a guidance scale. So the important point is this is no longer the true guided vector field, but as we'll see, it's actually still not that bad. And in fact, it might even do better in some subjective sense down the road by cranking up the signal provided by this guy right here. So this line of reasoning, actually, if you were to sort of develop it a little bit further, you would arrive at something called classifier guidance, which is sort of the original formulation of guidance that people used beyond this sort of naive guidance procedure. But we're not going to stop there. We want something else. We want classifier-free guidance. So what are we going to do? OK, let us simply plug Bayes' rule in again to this term. So where are we right now? We are at ut of x given y is equal to, what is it equal to? It's equal to ut of target. Oh, there should be an x here. X. Okay. Ut of target x, our unguided vector field, plus bt times our guidance scale. You know what? Let's put the guidance scale before. Let's say it's w times bt times our classifier. OK, now let's re-express this guy in terms of Bayes' rule again. So where was that term? This guy was here. So we can say that this classifier term, or again, as Tony pointed out, this is the classifier. But I'm just going to sort of abusive notation say this is the classifier term. This guy is equal to this guy minus this guy. So I'm going to replace this is equal to ut. You know what? This piece of chalk is not as good as the other one. We're going to say this guy is equal to ut of target. There we go. Plus w bt times, plug back in Bayes' rule, log pt of x minus log pt of x given y. Okay, what happens? Well, nothing yet. I'm going to add in another thing and subtract another thing. We're going to say ut of targets of x, and I'm going to say minus w at x plus w at x plus w bt times this guy All right, and now we're going to rearrange some terms. So we're going to, what are we going to do? We're going to combine this guy right here with, we're going to combine this guy right here with this guy right here. The sign is not what I want. The sign, aha, it should be the other way. This should be pt of x given y. And again, if you see a mistake, if something's confusing, just call me out and we'll fix it. So I just goofed right there. So this should be the other way, like that. OK, so what are we going to do? We're going to combine this minus guy with this minus guy right here. And then we're going to mush these guys together. And what we're going to get is ut target of x minus w times at of x plus bt times the unguided score. Okay, and then we have two remaining terms kicking around, plus w times atx plus, plus the actual guided score. Yeah, Tally.
What happens between the
Second and third lines. OK, so I basically shoved this guy over. Oh, yeah, OK, so there was a mistake that I updated here. Forgot to fix it here. So let me fix that. So this is.
where do the A terms come from?
Yeah, good question. So notice I added it and subtracted it. So it's 0. I've added 0. And I've done that to group things together so that we get what we want. Yeah, great question. All right, so I've grouped them up together. And now let me observe that what is this guy? This guy is ut target of x. And this guy is, this is ut target of x given y. And so we arrive at let me move the equal sign this way. 1 minus w times ut target of x plus w times ut targets of x given y. Right. OK, so we've rearranged and we've obtained that this expression right here, this u tilde, our sort of classifier guided u tilde rearranged, can actually be rearranged to obtain this classifier free form, right? You have a question, Cole? No, you're good. Right, so instead of that classifier term kicking around, now we simply have our unguided and our guided terms, which is simpler. This is kind of nice. This is kind of a nice result here, although we sort of constructed this quantity so that it does have this form. But let's go to the slides just for the sake of time. Right, so we've identified this identity right here, so which classifier free guidance. Again, we arrive at this end result here. We can write this classifier free guidance vector field ut tilde as this sort of weighted average between our unguided and guided vector fields. And this is classifier free guidance. OK, but why do we care about this? What's so great about this? I still haven't told you yet. You should still be skeptical. And furthermore, it seems like we still have two terms, right? It'd be nice if we only had a single uniform term. Because as is, I would have to obtain the unguided and guided vector fields before I was able to use this. And so the idea with classifier free guidance training is, well, the unguided vector field is just the guided vector field conditioned on nothing. And the observation is that nothing is something. And so I'm going to say that the unguided vector field is just the guided vector field guided on nothing. So we've used this null/var nothing character to denote the absence of guidance. And the idea is now we are going to train a single model, denoted ut theta of x given y, just like in the regular guided case, but adapted for this CFG case. And how do we adapt it? Well, we can start with sort of the same backbone as our guided objective by regressing ut theta of x given y, this guided model, against the conditional vector field. And we can write the same thing as before, but notice if we don't include this guy right here, then we are never going to end up with y being this null character, right? We're never going to sample from our data loader and see, oh, the prompt is nothing. You know what I'm saying? We have to artificially introduce this ourselves. And so we're going to introduce this hyperparameter eta. And we're going to say with probability eta, we're going to sort of mask out y. We're going to replace y with the var nothing character, or the null character. And this allows our model to see this null character at training time, and thus allows us to learn ut theta of x given y over not just our set of y's, this mathcal y, but also this var nothing character. All right, that's great. How do we sample with it? So to sample, what we're going to do is once we've trained this thing right here, we're going to select a prompt, y, in our universe of y's. Or if we want to do unguided sampling, we're just going to take it to be this null guidance. We're going to choose a guidance scale, w, more than 1. We're going to initialize as before. And we are going to simulate the ODE corresponding to u tilde of x condition of y, or guided by y. And again, it's just this expression right here. And we're going to simulate that from 0 to 1, like we usually do. And we are going to get our classifier-free guided samples. So you might be asking, why do I care about this? Why should I ever use this? What good is this if it's not sort of theoretically justified in the way that sort of the traditional guided sampling that we discussed first was? And to that, I say, look at this image. So this is from the lab. We have sampling at 3 different guidance scales. So the first is w equals 1.0, which corresponds just to traditional theoretically grounded guided sampling. We can see that it looks OK, but some of the digits are not quite there, right? But as we increase the guidance scale, as we go to w equals 3.0, w equals 5.0, we sort of get much cleaner generation. So the perceptual quality increases. And perhaps if we lose anything, it's some amount of diversity. But the things we do generate seem to be cleaner and nicer. And the source of this image, as you see, is lab 3. So you'll be generating this image yourself in lab 3. Right. OK, so real world example, please. Let's go to the next slide. This is from the original classifier-free guidance paper. And you can see that they're asking about corgis here. And if you do no classifier-free guidance, in other words, set w equal 1, then you get, I mean, these are, it kind of matches the prompt, but it's not great. We don't really see the corgi prominently in the picture. And then if we crank up the guidance scale, we get these great pictures of corgis. And again, this is the sort of theoretically grounded one. And this is the one that seems to give images of sort of higher perceptual quality. These seem more corgi-like to us. All right, so question. 2 questions. Question. Yeah. What was the classifier that we used? What do you mean by what was the classifier? So are you asking about, what is the y? Oh, so yeah, good question. So y is the identity of the digit. So 0, is it 1, is it 2, 6, 7, 8, 9, or nothing? Yeah, cool. Yeah, that's exactly. That's. Yeah, so people have, yeah, so you're right. So 1, it's not sort of grounded in the way, it's not sort of principled maybe in the way that's setting w equal to 1 would be. There is a lot of literature on why you get better results when you crank up the guidance scale. One intuition is that it's sort of a crude way of approximating like low temperature sampling. So you're sampling from the higher density regions, and so you sort of trade off the diversity of your samples with the quality of your samples. And I think people have shown that you kind of trade off, you can sort of measure diversity in perceptual quality, and you can trade these off by using guidance like this. With GANs, people look at sort of like truncating the initial sample and they get a similar effect. Like, it's kind of a crude way of sort of trying to not sample from the tails of your data distribution, only sample from the kind of the middle of it. That's the rough answer. The longer answer is that there's a lot of research and it's kind of an open question, to the best of my understanding. Right, okay, so we have about 10 minutes left before I'll hand it over to Carl's. Let's talk about architecture. Right, architectural considerations, and again, this is for our running example of image generation. Okay, so before we get into this, let's ask, what does an image look like? I forgot, we discussed it briefly in the first lecture. So just so that it's fresh in everybody's minds, an image lives in this Euclidean space, which we're going to define as we're going to factor into 3 dimensions, the first of which is the number of channels. So if this was an RGB image, this would be 3, a red, blue, and green RBG. This would be, there'd be 3 color channels, red, blue, and green, RBG, and then H and W denote the number of pixels for the height and width of the image, respectively. So in lab 3, we'll be working with MNIST images, which are black and white. So these would just have 1 alpha channel. Sometimes you'll see images with 4, an RGB, and then also an alpha channel as well. And sort of the observation is that an MLP, a multi-layer perceptron, otherwise maybe some people refer to it as as a fully connected neural network, this is going to be insufficient in these really high-dimensional image spaces. These things quickly become thousands and tens of thousands of dimensions very quickly, and you're not going to be able to throw an MLP at that in an efficient way. And so, as a result, we need to actually think about what this model should look like. And we're going to explore 2 choices. We're going to look at UNets, which are what we use in lab 3. These are based on convolution. And then we're going to look at diffusion transformers, which are sort of the more modern, recently popularized approach, which is based more on attention. We want you to pay attention as we throw a bunch of pictures at you. This guiding variable y, how is it encoded, embedded, and processed by the model, right? So instead of just throwing it into an MLP, we have to be careful that we're actually kind of using it in a way that makes sense. This is kind of the name of the game, is really how are you actually featurizing y, how is it being used by the model? Right, okay, so let's start with the UNet. We'll start with the UNet from lab 3. This is sort of a UNet architecture. And again, UNet is a family of architectures, sort of all just united by the fact that they all kind of look like a U, as we'll discuss in a sec. But the UNet from lab 3 is the one we'll be talking about right now, and it's a simplified UNet, which we think sort of makes the most sense for learning purposes, in which we've sort of constructed and put in lab 3. You can look at the code when you work on lab 3, but we're just going to give a brief overview right now. So as I said earlier, the UNet architecture is based on convolution. So in this case, let me just say, the images we're working with are MNIST images. So this is what you'll see in the lab. The number of channels is 1. It's just an alpha channel. And they're 32 by 32 pixels to start. And our labels, as somebody was asking about, are just 0 through 9, as well as this kind of null label. Right. So what's going on with the UNet? So at a high level, and we're just going to discuss for the sake of time at a high level here, XT is going in. It's going through the encoders. And each one of these encoders is sort of adding channels. So making the information on each pixel richer while decreasing the number of pixels. So we go down through the encoders, channels go up, pixels go down. We go through this thing called the midcoder. This is not standard notation at all. We just thought it sounded more similar to encoder and decoder for the sake of the lab. The midcoder preserves the number of channels and the number of pixels, and then it's going to go up through the decoders, and it's going to just reverse this process. And then we've attached these residual connections that allow information to just shortcut between these 2 things right here. And the 2 other things you should note is T is embedded. In the lab, you'll see there we use Fourier or sinusoidal embeddings. These are similar to positional embeddings used in language models. And then we also embed Y. Y is discrete here, so this is easy. And in the lab, you can take a look at how we do this. Right. Okay. So encoder, what does the encoder look like? It's 2 of these residual layers, which we'll talk about in a sec. So it just processes it, and then it downsamples it, increases the number of channels, decreases the number of pixels. Similarly, we have and I'm going through this fast just because I don't have a ton of time right now, but you'll get to explore this in the 3rd lab. So the midcoder has 3 residual layers, not super exciting. T and Y are fed into both of them. And the decoders essentially just reverse the operation of the encoders. They just upsample, so they go from maybe 512 channels by 8 by 8 pixels to 256 channels by 16 by 16 pixels, for example. And then the actual workhorse of our network, this residual layer, it's just, we're going to have this residual shortcut, and then we have 2 convolution layers plus some normalization. Here we use batch norm as well as an activation right here. And then between the 2 layers, we're going to inject this conditioning information. And T and Y have been embedded into some embedding space. And we are going to basically pass them through an MLP to convert this embedding dimension to the number of channels. And then we're going to add it channel-wise. And again, maybe this doesn't make sense right now. This is something that you can dig into during Lab 3. It's sort of the point of Lab 3. We pass it through another convolution, normalization, and activation layer right there, add it to the residual connection, and then just send it on its way. OK, that's the UNet. So the next thing we'll be talking about is a diffusion transformer. This is an alternative to a UNet. It disposes of the idea of convolution, mostly. And it says, let's use attention. Everybody loves attention these days. How do we employ attention when we're working with images? The big idea is take my image. I'm going to chop it up into little patches. I'm going to featureize each patch. And then I'm going to attend between the patches. So this is based on what's called a vision transformer. This was originally used in, for example, classification. And the idea is we take this image right here. It's of this, this cityscape right here. I'm going to patchify it. This is the first operation. I'm going to sort of lay out all the patches in a sequence. I'm going to embed them into some common embedding space. And I'm going to attend between them and just pass them through. And here they have some transformer-like encoder. And at the end, you have some head that just kind of reads your states at the very end, and then just constructs logits based on them, and then uses that for classification. And so the diffusion transformer people were like, "This is great. Let's take this and adapt it to a diffusion setting where I'm trying to predict what my next step should be." The diffusion transformer their formulation of diffusion is sort of is sort of more of the, in this case, they're predicting a noise in a covariance matrix here. It's slightly different than our formulation. They're equivalent, but their output looks slightly different than what you would see if you were to implement that in our context. But the idea is essentially the same. Patchify, embed, and then pass it through these attention blocks. All right, so I only have a few more minutes before I hand it over to Carl's. But I want to briefly just switch topics and just discuss a general design pattern that's sort of orthogonal to whether or not we use a UNet or a diffusion transformer. And that is whether or not we train our model in the latent space of some sort of autoencoder, some sort of variational autoencoder. And the idea is just that. Let's go to the next slide. The idea is that kind of frequently I'm working with, for example, images, and there are all these sort of high-frequency, imperceptible details that I don't really want my generative model to have to worry about. And so the idea is to kind of farm out some of the computational power to a large, usually pre-trained autoencoder, which is going to compress down my image into a space that allows the generative model, if trained in this latent space, to really just focus on these coarse-grained, perceptually relevant features. So here we have just an architectural diagram from this paper, high-resolution image synthesis with latent diffusion model. This is a paper from NVIDIA from about 2 years ago. I guess it's 2025 now, so maybe 3 years ago. I think it's from 2022. They have a UNet. It's in latent space. You'll notice that their UNet has attention. Ours doesn't. There's a whole bunch of variants of UNets. But the whole thing lives in a latent space. And to sample, they would sample normally, except the thing you end up with is a latent sample. And they just pass it through a decoder. And the data set they train on is just an encoded version of the data set. Right. So again, this is not an alternative to UNets and diffusion transformers. This is an alternative design decision that is often used in combination. And in nearly all state-of-the-art models, for example, image generation, people will train in latent space. All right, and just to end, we have kind of a lot going on here. Let's just do a quick case study. This is Stable Diffusion 3. The idea is Stable Diffusion 3 does use a pre-trained autoencoder, and then I guess for those of you who are wondering, yes, they do train with nearly the exact same objective that we have shown in class. They just call it V sub capital T theta instead of our UT superscript lowercase t theta. But yes, this is conditional flow matching. This is exactly what they use here. The only difference is that their parameterization of UT theta is significantly more complex than the MLPs we've been working with. Just to be brief here, really a lot of the special sauce here is in the use of these pre-trained clip and T5 XXL embeddings. Clip is essentially an embedding of it's sort of a shared representation space of images and text, and allows you to generate these coarse-grained text embeddings that are perhaps useful to work with when also working with images. And then they also use these embeddings from one of Google's T5 language models to basically obtain some sort of sequence-level contextual information that they can then incorporate into their attention. And so they define this MMDIT, this multimodal diffusion transformer block, which generalizes the diffusion transformer that we talked about on the previous slide from sort of classification-based conditioning to more general conditioning on text prompts, for example. And they have this complex architecture that you can dig into here that really is not much more than what we've already seen on the previous slides, but is very busy and colorful, and is probably best viewed on your own time. And yeah, okay, so with that, before I hand it over to Carl's, our next class is on Thursday. This is one of the most important classes. We want you there for it. This is two guest lectures. The first is on robotics, and the second is on protein design. This is not one joint lecture. It's in this room. It's next Thursday, I believe, from 11 a.m. to 12:30. And then as a reminder, Lab 2 is due on, I think, Wednesday at 5 p.m., we said. And we have office hours on Tuesday and Wednesday. So please feel free to come to office hours, ask us about Lab 2, ask us about the notes, about lectures, about any questions you have. And the one thing to keep in mind is the Wednesday office hours are actually in this room, not 37212. Yeah. So with that, I'll hand it over to Carl's. Peter, do you want to introduce Carl's while I get you set up with the mic and stuff? Are there any questions in the meantime? Yes, it's at the end.
You talked about for classifier guidance how you could basically train UT target of X by conditioning on nothing, but in practice, how do you do that sampling? It's more like conditional distribution, but then you're
Hold on. Would you mind helping me get Carl set up so I can ask the question?
All right.
Sorry.
Thanks.
That works?
All right, cool. So thanks, everyone. So we're now going to switch gears a little bit. And what we want to show you is a bit how the frontier of research in algorithms about flow and diffusion models look like. And that's why I invited Carls, because has done excellent research on that front. And he's going to talk a bit about things that are related to what we talk about today, about classifier-free guidance, but an extension of that to reward models. I just want to quickly introduce Carls. So Carls is a senior researcher at Microsoft Research New England, so right across the street. He graduated from NYU with a PhD, was advised by Juan Brunner, and he also worked for 2 years at Meta as a student or visitor, for a visiting researcher, right?
Yeah.
So maybe let's give a quick round of applause and thank Carls that he came here to teach us about diffusion models. Thank you.
Thanks, Peter. I'll be giving you an overview on reward fine-tuning for flow and diffusion models. And this presentation will be mostly covering or related to this paper, agent matching, fine-tuning flow and diffusion generative models with my model is stochastic optimal control. So if you have some questions about what's in this talk, well, there will be some time for you to ask me. But you can also check out the paper, and I feel like, we tried to make it as self-contained as possible. So with that, I'll just get started. And the title of the presentation is Reward Fine-Tuning for Flow and Diffusion Models. And some other open questions that I'll be tackling, and just to set the stage for the talk. The first one would be, what's the best way to perform RLHF on diffusion and flow models? If you look at the LLM version of RLHF, people use PPO, DPO, and there are works that use PPO and DPO, in fact, for diffusion and flow models. But the additional structure that you have for diffusion and flow models allows you to use other algorithms, but also you have to figure out how you are actually supposed to implement all these techniques that you could also implement coming from LLMs. So there are these two things to be figured out, and I'll be talking a bit about those. This is just an introductory slide, so I'm going to be showing results or like applying most of these concepts to text-to-image models. So in theory, what we're starting from is like a pre-trained diffusion model. In this case, it's text-to-image. And we want to basically get better samples, and that can mean different things. In this case, of text-to-image, well, we want them to be nicer or like better in terms of like human perception, and also more aligned to the prompt. And then the second open question, neither the pre-trained model nor the post-trained one are actually amazing, but and then the second open question, which is very much related to the first one, is how do we solve stochastic optimal control problems in high dimensions? So stochastic optimal control problems are problems that we can use both to perform RLHF on diffusion flow models, which we'll see in this talk, but they can also be used for other applications. And in particular, a big one is sampling from anomalous distributions. So SOC, RLHF for diffusion flow models, very related, but SOC in a way covers other areas as well. Okay, so I'll go into fine-tuning setup. What do we start from, and where do we want to get at? We start from a pre-trained diffusion or flow matching model that generates a certain distribution p-base. You can think of our model as being conditional if you want, and most of the times it will be like that. And then we also have access to a reward model that has been trained either using human preferences, and that would be, just like you would do in LLMs. Or you can also think of reward models that encode conditional sampling. If you plug rewards of this form, where basically the reward is the log likelihood of some observable, then you'll end up performing conditional sampling, which is, as I understand, very related to what you discussed earlier on. So all of this is to say that when you fine-tune, you can also aim for doing better conditional sampling than what you would do at inference time or with other techniques. And then the goal is to modify the pre-trained diffusion model so that it generates from p star, which is proportional to p-base, say p-base here, times exponential of R of x. If you look at this one-dimensional plot on the right, you can see that p-base would be the distribution that you see in green. And the trajectories that you see are here, like trajectories for an ODE that samples from p-base. So that would be the trajectories for the base model. And we also have this reward model that gives us this orange dotted curve, which essentially is telling us how we need to modify our pre-trained distribution to obtain the fine-tuned distribution, which is the one in purple. So the fine-tuned model essentially will be one that samples from this fine-tuned distribution, which is proportional to p-base times exponential of R of x. And you can see that the trajectories of the fine-tuned model have been modified with respect to the trajectories of the pre-trained one. These would be the OD trajectories, and in lighter purple you can see trajectories that are sampled from an SDE. Basically the interplay between SDE and ODE will be something that will be very important for fine-tuning, as you'll see later on. Okay, so just to set the notation straight and to be clear what I'm referring to when I write some variables in the slides, I'll give a very brief overview of flow matching and diffusion models. As you know, we can start from, like, the pre-training happens by choosing samples from a Gaussian and samples from data. And then there's a reference flow. There's probably a different notation that you've used in this course, but reference flow would be just interpolation trajectories. And then what we learn when we pre-train is this generative flow, where the generative flow is given as the solution of this OD, where the vector field V is trained. The vector field V is trained by solving the regression problem that you're all familiar with. And then we know that when that happens, and if we learn the vector field V exactly, then the reference flow and the generative flow have the same marginals for all times. And in particular, they have the same marginals at final time. So that means that we're actually learning the target distribution. Now, I want to go into another way you can sample from once you have a pre-trained flow matching model, which is the generative SDE. In the previous slide, you can see I wanted to show this previous slide, but it's not showing, so I'm just going to go ahead. Yeah, in the previous slide, you can see that I was sampling from the flow matching model using an OD. Here, I'm going to sample it from using an SD, and the way to do it will be as follows. So say you have PT, which is the distribution of the reference flow, and this color graphic S is the score function. I think you've heard about the link between scores and between the score function and these kind of models. What happens is that you can express the flow matching vector field in terms of the score. So there's this relationship which is actually pretty simple. So the vector field, flow matching vector field, can be related to the score in a fine way. And then if you think of how you can use the scores for SDs, basically you can use the score to rebalance adding noise with a noise term. So what I'm doing here is I'm adding a noise term, which is with an arbitrary diffusion coefficient, but then I'm canceling it out by adding the corresponding term involving the score in the drift. And then since there's this connection between the score and the flow matching vector field, once I replace the score by what it is in terms of the flow matching vector field, I obtain this flow matching generative SDE. So this is a generative SDE that still samples from the appropriate distribution. So if you look at the marginals for all times of this, the solution of this SDE, it still has the same marginals as the reference flow. But in this case, what we're able to do is we're able to use an arbitrary noise schedule. And this is something that we will really like to do in order to set up the fine-tuning problem. And then some more notation, which I would like to avoid, but unfortunately later on I'm using this kind of variables, is once you have this SD, you can just rewrite it. I've talked about flow matching vector field and score functions. Basically, whatever you have in terms of one, you can put in terms of the other. So here I'm rewriting the flow matching generative SD in terms of the score. And the only thing I want you to remember here is this variable eta t, which will appear later on. I'll refer back to this. But yeah, from this slide, the only thing to take home is that you can sample a flow matching model with an arbitrary noise schedule. Now I want to go into stochastic optimal control. I'll later tie in this with flow matching. This is just a generic introduction to stochastic optimal control. This is a problem where you start from an SD, which is the control SD that you can see here below the objective. And this SD has a base drift, a noise schedule, which again is arbitrary. And then it has this other term, which involves the control function. And you can see this control term as a perturbation to the original base drift. And the way you want to learn the control is you want to essentially trade off minimizing the state cost and the terminal cost. So you want to make those small while making this perturbation term not too large. So the control cost basically takes care of your perturbation not being too large. And when you think of stochastic optimal control, there's an important object that we'll be using later on, which is known as the value function. The value function, also known as the cost to go, is essentially the control objective that you have once you're at a certain point x at a certain time t. And it has these two expressions. I know it's stumping you a lot of stuff at the same time, but I'll be using those. Just keep in mind this, that the value function is an important object for stochastic optimal control. And now I've presented stochastic optimal control, but I haven't told you a simpler way to understand it, which is that stochastic optimal control is just KL regularized reinforcement learning. For those of you that are familiar with PPO or with how RLHF works for LLM, what you're solving when you do RLHF for LLMs is actually a KL regularized reinforcement learning problem, where, again, you're using the reward you want to optimize, but you also have a KL regularization term that avoids your fine-tuned model from deviating too far from the pre-tuned one. And now I'm going to show you very briefly and a bit schematically how this is the case for stochastic optimal control. Again, no need to go into depth here, and this is a pair of slides you can skip if you want. But basically, to get there, I'm just going to use this notation where PU given x0 and P given x0 are the conditional probabilities of the control and uncontrolled process. The uncontrolled process is one where the control is set to 0. And there's a theorem in stochastic calculus, which is known as the Gersonov theorem, which actually lets us write the control term in the control objective as the KL divergence between these path probability measures. So with that theorem, we can essentially rewrite the control objective like this. And this looks a lot more like a KL regularized RL problem, because if you think of it, this first term would be just the expectation of the reward, and then the second term would be the KL regularizer. And if you're familiar or you've seen this kind of problems before, the solution of such KL regularization problems is of the following form. You essentially have like the optimal distribution is proportional to the base distribution times the exponential of the reward. So that holds just as well in the case of path measures. And we're almost there. I'm just going to, copying this from the previous slide. What we need to do in order to basically get what the optimal solution is without conditioning on the initial state x0 is we need to find the normalization constant of this term on the right-hand side. And in order to compute it, we essentially see that the normalization constant ends up being expressed in terms of the value function. This is, again, if you recall, I defined this object value function, which had two characterizations. This is the second one. And once we plug this normalization constant, which importantly only depends on x0, we obtain this final characterization of the optimal process in terms of the base process and the rewards, as well as the value function. I know this looks a bit ugly, but we're going to make it simpler now, and we're going to apply it to the fine-tuning case, where things will be significantly simpler. So if you want to apply all this stochastic optimal control framework that I've introduced to the fine-tuning case, what you're going to do is you're going to set the state cost f to 0 and the terminal cost to be minus the reward. So once again, you see here that what we're doing is we're trying to minimize minus the reward, which means maximize the reward, while keeping the perturbation or the control term not too far out. And then we obtain that the equation that I showed in the previous slide becomes this equation where the marginal process, the marginal of the optimal process at the endpoints x0 and x1 takes up this form. Of course, if you remember what our goal was, and that's something that I introduced in the first or second slide, we wanted a distribution P star. We wanted to sample from P star, which is proportional to P1, P of x1 times exponential of Rx of x1. So what bothers us here is that there are these x0s that are here but shouldn't be. And we're going to impose some conditions that will actually be implementable to make sure that those x0s disappear. The condition that we need to impose is this memorylessness property. So we define a generative model, a generative process to be memoryless if x0 and x1 are independent. That means that P of x1, x0, that's the marginal for the two endpoints, is actually independent and decouples into P of x0 times P of x1. Once we have this, it's just you can integrate out x0. If you do that, you see that basically you can really get rid of it and end up with what we really wanted, which is that P star of x1 is proportional to P of x times exponential of R of x1. And OK, so we know that this is the condition that the base process must satisfy, but how do we actually get this condition to hold? Is it even possible? And now I'm going to show that for the framework that I presented before, where there was this flow matching generative SD, we're actually able to come up with a way to make the generative process for the base distribution memoryless. And that's the proposition. Basically, there's a way to choose sigma, which, again, we could choose however we wanted. We had this freedom in order for this process to be memoryless. And the way you have to choose it is basically you have to choose it to be equal to 2 eta t. Remember, eta t is this coefficient that appeared before, and it's purely given in terms of the parameters alpha and beta that were used to pre-train the diffusion model. So basically, how you did the pre-training forces which coefficient you need to use to fine-tune. And then you can allow for a perturbation, which here is written as high. And this perturbation, yeah, essentially it can't be too small to negative because otherwise the condition would not be satisfied, but you can just set it to 0. And later on, we'll see that there are reasons to set it to 0. OK, now I'm going to tell you what happens if you don't choose a memoryless schedule to fine-tune, because you may think, OK, maybe this is all theory. Maybe you can actually use another noise schedule, and you don't need to go through all this to do fine-tuning for diffusion models. But actually, no. This is what the pre-trained model looks like, and this is, again, the target that we're aiming for. And this is what happens when you're fine-tuning with a sigma, with a noise schedule which is not memoryless. In particular, here we have a small noise schedule, and we see that the distribution that we generate when we solve the stochastic optimal control problem for this noise schedule is actually drifting away a bit from the base distribution and towards the one that we're targeting, but it's actually very, very close to the base distribution still. This third plot shows what happens when you use fine-tune, say with a sigma, which is 1. And again, here you're a bit closer to what you're targeting, but you're still not quite there yet. And finally, when you fine-tune with a memoryless with the schedule which is memoryless, and that's in particular the one where you're having that sigma squared is just 2 beta t, you're actually really targeting what you were aiming for. So this is just to say that you have to solve a stochastic optimal control problem, and you have to choose a memoryless noise schedule when you do so in order to for the solution that you're targeting to be the right one. Okay, and then this is not the end of the story, because normally when you want to do inference on a fine-tuned model or like a pre-trained model, people tend to prefer to do inference with the zero noise schedule, because then they can use ODEs to sample, and numerical methods for ODEs are in general much better than numerical methods for SDs. So once we have our fine-tuned model that we've fine-tuned by solving an SOC problem with a memoryless noise schedule, we want to still be able to do inference on the fine-tuned model with the zero noise schedule. So we want to be able to do inference on the fine-tuned model just like we were doing inference with the pre-trained model. And in order for this to hold, we actually have no choice. We need to use the memoryless schedule, which is given by sigma t equals square root of 2 eta t. Yeah, this is the theorem that we show. Feel free to check out the proof in the paper, but I won't go into detail on this. But this is just to say that there is a pre-trained, there is a preferred noise schedule we want to use when we do fine-tuning. And for those of you that were curious about, oh, before this theory came about, people were still fine-tuning models, and there are works that do that. And this is kind of a coincidence, or like a, yeah, I would say it's nice that people were actually choosing the right choice, because when you look at what the memoryless noise schedule looks like for DDIM, so that would be like, for example, for Stable Diffusion in versions prior to Stable Diffusion 3, they were using DDPM to fine-tune, and DDPM is actually the memoryless noise schedule for DDIM. But when you go to flow matching models, actually no one was using the memoryless noise schedule for anything, because yeah, flow matching arose as a method that was natively ODE based, so no one had really played around much with SD versions of flow matching. Okay, check out the time. Okay, yeah, we have some time. Finally, to give you the whole detail of how you go from the control problem to the flow matching problem, I'm just going to show the translation between the two languages. Recall that the drift for the flow matching vector field, sorry, the diff for the flow matching SD was this one. And then once we plug the memoryless noise schedule, we end up with this kind of drift, which simplifies substantially. And then we essentially want to, yeah, we have that these choices must hold. Essentially, we regard B as the drift that we were using for the base model, and we regard the control drift as the drift that we're using for the fine-tuned model. So if we isolate U from these two equations, we obtain this relationship between the control U and the difference between the fine-tuned flow matching vector field and the base flow matching vector field. So when we want to fine-tune, what we're going to do is construct a control by subtracting the fine-tuned flow matching vector field minus the base flow matching vector field, and then we're going to apply a stochastic optimal control solver to solve that control problem, while keeping always this kind of equation whenever we want to evaluate the control. Okay, so now I'll talk a bit about methods for stochastic optimal control. And first I'll talk about the adjoint method, which is what people have been using classically to solve stochastic optimal control problems with neural networks. The adjoint method can be seen from two perspectives. First, I'll introduce the discrete adjoint method, which uses this loss function. And if you think of it, this is what you have in the expectation of the control objective. So what you're doing for this method is you're simply parameterizing the neural network, the control with the neural network. Then you're taking rollouts for that control. So you're just sampling trajectories with that control. And then you're evaluating this quantity, which again has the control term and then the state cost term and then the terminal cost term. And you keep all of this in the computational graph, and then you backprop through all of it to obtain a gradient with respect to the parameters of the control. So this is really very intuitive, and this is what people have been doing, and it's been working roughly okay. There's another way to see this same algorithm. So this is another way to compute the same gradient, which is equal up to numerical errors. So if you were to take very small step sizes when you discretize the ODEs and when you discretize this objective, both would look the same. And this is a method where you can see that what you're doing when you're doing the adjoint method, and this is something that we call continuous adjoint method or basic adjoint matching. Yeah, these are all different names we give to this algorithm. You see that what you're doing is you're solving a regression problem where you're regressing the control U that you're learning into an object, which is sigma t transpose times this vector field A. This A is the adjoint state, and it satisfies the adjoint OD. That's why all these methods are known as the adjoint method, because either implicitly in the case of the discrete one or explicitly in the case of the continuous one, they're leveraging this adjoint state in order to learn the control. Some more details on this method. This is the same as before. There's an interpretation that you can have for the adjoint state, which is essentially the gradient of the cost to go for the trajectory with respect to the position at time t. And once you observe that this holds, and if I tell you also that the optimal control takes up this form, so it's basically minus sigma transpose times the gradient of the value function, what you're seeing is that when optimizing the basic adjoint matching loss, what we're aiming for is fixed point of this equation. So we want that U star is equal to sigma transpose times the gradient of the expectation here that you have here. And since there's only one solution to this fixed point equation, this is something that we show, when you're actually at the point which is the critical point of this loss in expectation, then you're at the optimal control. I know that this is a bit rushed, but yeah, that's roughly how you understand that the basic adjoint matching loss is doing what it's supposed to. And now I'm going to present adjoint matching, which is basically slight modification of the basic adjoint matching loss, which according to our experiments was the method, the SOC solver, that performed best in these large scale experiments to solve the control problem that I presented in slides prior. Okay, this is the adjoint OD that I just described. And we came up with this lean adjoint OD where we essentially canceled out a couple of terms here. So the term sigma t U transpose A with the term gradient of 1/2 of U norm squared of U are gone, and we just have this simpler OD. And you may wonder, okay, but why are you doing this? And the reason is that in practice, what we want is, what's a big issue when you run these algorithms is variance. And when you're solving an ODE that has a lot of terms, the solution of the ODE will have higher variance, most likely. And that happens. And it's higher variance by orders of magnitude, by a couple of orders. So in getting rid of those terms, we're essentially getting rid of a lot of variance. And that really helps. And why can we even get rid of those terms? It's because if you think of what happens with those terms at the optimal control, they're already 0